Okay, let's continue talking about the pH scale in subtopic number 5.3. In this video, we'd like to talk about this point here. To undertake calculations using the relationship pH equals to negative log of concentration of hydrogen ion or hydronium ion and its rearrangement, which is concentration of hydrogen ion equals to 10 to the power of negative pH. Let's look at that. So in the previous video, we have established that in the neutral solution, there is 1 times by 10 to the power of negative 7 moles per liter of hydronium ion or hydrogen ion, they're interchangeable, and equal concentration of hydroxide solution. So if you plot one number which is 1 times by 10 to the power of negative 7 into this equation, the rearranged version of the formula that was introduced before, you would find that concentration of hydroxide ion would be the same as the hydronium ion. Hence, you would have that relationship, which I would highly recommend you to write down. So at pH of 7, you would have the same number of OH minus as H plus. Whereas if you look at acidic range like pH of 4, there are a lot more H plus present or hydronium ion present and a lot less of OH minus. Whereas in basic solution, say ammonia, that would be, I don't know, let's say pH of 12, could be a bit less. There is a lot more concentration, higher concentration of OH minus compared to H plus. But what's important for you to know is that given the concentration of hydronium ion, there would be, and if you multiply the concentration of that to the concentration of hydroxide ion, that would always equal to 10 to the power of negative 14. So on the next slide, we'll convert this information into logarithmic scale. Well, we could keep talking about concentration, but concentration is not really a good looking number. So someone, I forgot the name, but the scientist thought of making a little simpler number, which is going to be pH, by using base 10 logarithm. Because base 10 logarithm and 10 to the power of notation, they kind of cancel out each other. Something that you must know is that pH equals to negative log of concentration of hydronium ion or hydrogen ion, whichever is fine, it's the same thing. So for example, if you had a HCl solution which happens to have 0.001 molar as its concentration, then you can plot that number into the formula that was given there, negative log, and then put the number in. Then you would get pH equals to 3. As you can see in this diagram, I'll zoom in here, that if you had 0.001, this one here, like what was given in the question, you will get pH 3. That also equals to 10 to the power of negative 3 as its concentration. 0.001 is going to be producing pH of 4, 0.00001 is going to be 5. Something that you would notice is that there's some increment here in concentration, or actually decreasing in concentration. 0.001, and if you divide that by 10, you will get 0.0001. Divide by 10, you still get the same thing. You would keep increasing the number of zeros in decimals. If you look at scientific notations of it, 10 to the power of negative 3 becomes 10 to the power of negative 4. because there's 10 times difference between these two. That also equates to pH. So what I'm trying to say is that there's a large difference in the number of H plus concentration. Okay, 10 times difference is what you should notice if you look at pH. So 1 pH scale differences equates to 10 times difference in the concentration of particle of H plus ions or H3O plus ion. How would you complete this? Well, you just have to again use the formula negative log of concentration of hydronium ion that's given to find pH. What I have done here is that well, you can find pH. You can pause the video and try doing that. We have already established that 0.001 concentration would give you pH of 3. And on the other side of this table, you can find 0.010. So it's 10 times more concentrated than original concentration. But the concentration doesn't always come in those, I guess, well-rounded number. So you could have 0.002, 0.003, and so on as concentration. And if you keep putting those numbers in, you can get pH like so. But you can see that then 0.010 ended up with pH of 2. So this also proves that 10 times of the concentration would produce one different scale in pH scale. All right. Formula so far covered are those two. What I also want to mention here is that you can also find concentration of hydronium ion from pH. So reverse of finding pH from the concentration. Formula here is the very, very important one. This is something you should highlight, underline, everything. So concentration of H plus can be found if you do calculate 10 to the power of negative pH. On your calculator, to do exponent, you might need to use that hat symbol. That means exponent on the calculator. This is an example. Find a concentration of sulfuric acid with pH of 4.5. Only thing you have to do is to use this formula. If you plot 4.5 into where the pH is, you should be able to find this number. Now you can stop there, you should still get the mark, but if you want to get an extra mark in finding the right scientific notation, right significant figure, you need to look at the question. So 4.5 is what's given, which is in two significant figures. So you might want to put your answer, final answer, in two significant figures. In this case, 3.2 instead of 3.16. If you're working in decimals, 0.000032 would be a number in two significant figures, but it's not really a good looking number. So let's use scientific notation here. Okay, final example here. How would you calculate the pH of 0.10, two significant figures, molar sample of sodium hydroxide? Notice that it's not an acidic solution. So NaOH would be producing very basic solution. You would also know that the pH is going to be higher, more than 0. How would you do it? Firstly, you have to convert the concentration of hydroxide ion to hydronium ion by using this.
rearranging that first formula that was introduced and plotting the number, which is 0.10, into where the hydroxide ions concentration is, then you can find concentration of hydronium ion as 1 times by 10 to the power of -13 moles per liter. After you finding that, you can just calculate pH from that formula. pH equals to negative log of hydronium ion. You just plot the number in and you find the pH. Voila, it's pH of 13, which is what you were expecting before as well. So a bit of summary here. pH scale works as logarithmic number. It's not gonna the concentration doesn't always equal to what do you call that, linear increment. It's gonna increase, and the pH would kind of equates to that. And pH, if it's acidic, less than 7. If it's basic, it's more than 7. And only pure water can be pH of 7. Sorry, I shouldn't say just water, but something that's not acidic nor basic will be pH of 7. Make sure you can calculate things using these three formula. And we'll watch this video in the lesson. So make sure you practice all that before the practice test that's going to happen soon.